Hello everyone, my name is Hannah, and today I will be presenting an overview of electrical engineering for my EX1 class. We're going to dive into the current state of art of this field and talk specifically about electronic circuit design, which is an electrical engineering subfield. So sit back, relax, and enjoy this presentation. To start off, I would like to give an overview of what will be covered in this presentation. I will first introduce electrical engineering as a field, and then I will talk about what electronic circuits are. And from there, I will provide examples of the current technologies and potential future growth in this field. Finally, I will end with job prospects for anyone who is interested in becoming an electrical engineer. First is an introduction to electrical engineering. What is electrical engineering? I'll be using the abbreviation EE to talk about electrical engineering. Ultimately, EE is a discipline focused on taking theoretical knowledge and applying it to analyze and solve problems by designing and implementing functional electronic systems. So what does all this mean? Basically, it just means understanding how electricity works and using it to build systems. Now, applications of electrical engineering. What do electrical engineers actually do? They essentially power our world. EE can power grids that light up cities and build microchips inside your phone and more. Figure 1 shows some applications of EE, such as power generation using solar panels for a house. Another example is nanotechnology, depicted in Figure 3, which is the design of ultra small, high performance devices by manipulating materials at the atomic and molecular scale. And EEs can contribute by creating ultra small transistor processors or nanostructured batteries. In fact, we interact with applications of EE every day. Think about your phone or the lights in your room or even traffic lights. Perhaps you have a biomedical device implanted inside of you, such as a placemaker or an electronic vehicle, or communicate via satellite communication, which is basically what happens when you make a phone call. All those things exist because of electrical engineers. So, as you have seen, electrical engineering is a broad field, and I cannot cover it fully in one presentation. So today I will focus in on electronic circuit design, which is a subfield of electrical engineering. What is electronic circuit design? Electronic circuit design is the process of creating layouts and functions with electronic components to achieve specific tasks. Engineers select and arrange parts like resistors and optocouplers into structures such as DC-DC converters, which can help change voltage levels. So, for example, converting a 28 VCD to a 5 VCD, which helps with more stable power supply. And also there's discrete I/O stages, which manage input and output signals using isolation and switching. So these designs not only ensure circuits are reliable and efficient, but also allow different parts of a system to communicate safely, making them essential for powering and protecting modern technology. So figure 4 here shows an electrical circuit diagram, and it's basically a design for an electrical system that can be used in modern electronics. So, what are the applications of electronic circuit design? Well, electric circuit design engineers are the people who can plan and build the brains of electronic devices. Instead of thinking about the whole phone or computer, they focus on the smaller parts inside, like the circuits that control power, process information, or send signals. They design simple circuits, like amplifiers that make sound louder, digital circuits, like the chips in computers, and mixed ones that combine both. They also create the boards, such as PCBs, that hold all the parts together. Their work shows up everywhere, in phones, cars, airplanes, medical machines, and even robots. In short, they make sure electronics are small and reliable and able to do the jobs we need them to do. Now let's talk about some of the current technologies related to electronic circuit design. So, today's electronic circuits are becoming smarter and smaller and more powerful thanks to exciting new technologies. Engineers are using materials like altermagnets, which are magnetic materials that allow spin polarized currents without external magnetic fields, which enable faster and low power memory in computing systems for applications like data storage and spin-based processors. Basically, this means that it moves data faster without needing magnets, which could help memory and storage devices. And they're also stacking chips vertically in 3D ICs in package on package, POP, designs, which are basically stacked semiconductors to save space and boost performance. However, keeping them cool is still a challenge that current electronic engineers and electrical engineers are working to solve. Okay, for some more technologies, in terms of the medical and environmental fields, lab on a chip, LOC circuits are tiny devices that perform laboratory functions on a microchip that can be used for things such as rapid blood tests, infection detections, DNA analysis, etc. It uses microfluidics, which are tiny channels that move and mix fluids to perform tasks like chemical reactions, separations, and analysis with very small sample volumes. LFCs make testing faster and cheaper and more portable by shrinking the entire lab process to a chip that's only a few millimeters to a few centimeters in size. And electrical engineers can make and take an active role in creating these. So, meanwhile, stretchable electronics are flexible devices like wearable health monitors and soft robots, possible by, and they use bendable materials and clever shapes that maintain functionality under stress. So, electrical engineers can help in making these stretchable electronics because they can combine the knowledge of circuits, materials, and system design to ensure that these materials and these devices are flexible and they can bend and twist and stretch while still working reliably. Okay, so now moving on to potential new developments and designs. So, a potential new development in EE involves solving a key issue. That is, the electronic industry is a significant contributor to environmental degradation, depleting natural resources and generating substantial electronic waste, which is also called e-waste. There is an urgent need for sustainable electronic circuit design. And so, our core goal is to minimize the environmental impact of electronic products while ensuring functionality. This is achieved by moving towards a more circular economy where materials are reused and recycled. While challenges exist, such as technical limits and economic constraints, this necessity creates immense opportunities for innovation in specifically materials and design of electronic circuits. So, for example, we are currently replacing toxic metals like lead and cadmium with safer non-toxic alternatives like tin and silver in circuits. So, secondly, we are focusing on physical design for sustainability. Figure 6 outlines the crucial guidelines for developing future degradable printed circuit boards, or PCBs for short. I know there's a lot going on in this diagram, so I'm just going to summarize it here. Basically, this commitment involves moving to materials like recycled plastics, bioplastics, and natural materials such as bamboo. For instance, replacing standard PCB fiberglass with bamboo composite has been shown to reduce carbon footprint of production by 62%. So third, we can adopt design for circularity. So this means that products must be easy to manage post-consumption, so after they are used. This includes using modular designs for simple component replacement, standardizing interfaces, and critically designing for disassembly to enable efficient recycling at end of life. By combining material innovation and life cycle management, the electronics industry can significantly reduce its negative environmental impact and build a truly sustainable future. So now potential future designs. A new direction in electronic circuit design is the use of machine learning, ML, to make chip design faster and easier. In fact, ML is taking place in almost every field in the United States. Traditional methods require exploring huge design spaces and running slow simulations. In electrical engineering, But machine learning can actually quickly evaluate performance and guide decisions, making advanced integrated circuit IC design more accessible. So deep learning models such as CNNs and GNNs can detect layout problems and predict congestion. Generative models, as shown in figure 11, can create high quality design samples. So GANs are a type of generative model and an AI where two models compete. So one creates fake data like images and the other tries to spot those fakes. So together they can kind of work together to learn and make very realistic results. And so reinforcement learning train systems to choose the best structures, place components, and size transistors. Overall, machine learning can help engineers produce better designs and more efficiently and finish projects faster. Okay, so now I will briefly go over some EE job opportunities in case you're interested in a career in electrical engineering. So this is a screenshot from the US Bureau of Labor Statistics with data from 2024. So I would like to bring your attention to two key elements. First, that the median pay for an electrical engineer in 2024 was $118,780 per year. And second, the job outlook for around the next decade is expected to grow 7% for electrical engineers. So that's more than the average growth for jobs in the United States. So those are just some things to keep in mind in case you're interested in a career in electrical engineering. Okay, so this brings us to the end of the presentation. I want to thank you guys all for watching until the end, and I hope that you learned something new. If you have any questions, don't hesitate to reach out. Okay, and then before I end this, real quick, I want to just put my references out there. I used sources from IEEE, some from Google. I also cited my images. And so if you are interested in learning more about anything covered in my presentation, all of it will be more detailed in these sources. So I recommend looking into these sources so then you can really dive into the field because this presentation was just an overview. So, yeah, thank you so much for watching. I hope you have a great day and goodbye.